Hello and welcome to Unit 10 from home. We are going to be talking about the two different types of sequences this unit. One's called arithmetic and the other one is called geometric. Normally this unit would be a lot longer, but we've tried to narrow it down to 3 days that we think are doable from home. So today, as you can see from this cover page, today all we are going to be doing is comparing sequences. So what is a sequence? A sequence is an arrangement of numbers or objects that follow a pattern or a rule. Okay, so when you were in elementary school and your teacher taught you how to count by twos or count by fives, that was a sequence and it was a pattern and you followed the same rule over and over and over again. Or when you started getting older and you started learning your multiples, so multiples of 2, that's also a pattern, and those are the two types of sequences we're going to focus on. So we could also do it with objects, pi, tree, next would become another pi, and I am not the best artist in the world, so just kind of bear with me, but there's my pi. All right, so a pi would come next. And you literally are just going to be looking and thinking, okay, what would come next and what's the rule and how do I get there kind of thing. So like I said, we are going to focus on two different types. The first one is called arithmetic. Some people say arithmetic, but it's not spelled the same, so it's arithmetic. And the other one is geometric. So let's focus just on arithmetic for right now. So consider the following sequence. Let's take a look at it. 4, 8, 12, 16, 20, and so on. What is something that you might notice about this pattern? Well, I notice that it seems to increase by the same amount every single time, and that amount is that it's adding by 4 every single step of the way. Okay, it never changes. It's always plus 4, plus 4, plus 4, and that's how I get to the next step. Okay, let's take a look at example 2. It also starts at 4, but now I go to -1, -6, -11, and so on. So what do you notice about this pattern? And what I notice is it is decreasing this time by 5, or you could think of it as subtracting 5. Those two numbers, that value that I am either adding every single time or subtracting every single time, is what we are going to be calling the common difference. Ooh, difference. Okay, so common difference, we are going to use the letter D to represent the common difference, and it could be whatever we add or subtract. Now, if we are adding something, obviously your common difference is going to be positive. If you notice that the sequence is going down or decreasing, then your common difference is going to be negative. So think of it as adding -5. Okay, so you could also think of this as adding -5. So adding to each number to get to the next term in the sequence. So we could always continue these sequences out by just using our common difference and expanding the sequence to the next term and the next term and the next term. All right, well, now let's focus on geometric sequences. So let's take a look at example 1 on this one. 5, 10, but 20, and then 40, and so on and so on and so on. What I notice about this sequence is that to get from 5 to 10, but then 10 to 20, and then 20 to 40, I have to be multiplying by 2. Okay, let's take a look at the next example. 64 to 32, 32 to 16, 16 to 8, and so on. I know that 32 is half of 64, and notice that this sequence almost appears to be a decaying sequence, right? We learned about exponential growth and decay last unit. So this would be multiplying by 1/2. So I know I kept thinking that it was dividing by 2, but we learned in the exponential unit, we never really want to think, what are we dividing by? We want to think, what did we multiply by? And so to get 64 to 32, we had to multiply by 1/2. 32 to 16, we had to multiply by 1/2, and so on. So because we are multiplying by something now instead of adding by something, we are going to call this the common ratio. I think last unit we called it the growth or decay factor, but we are going to use the letter R to represent our common ratio in the formula over the next few days. And all that is, that number that we multiply by is what helps us get the next term in the sequence. All right, so let's take a look. Each number in a sequence is called a term. Okay, so we have the first term of the sequence, the second term of the sequence, and the third term of the sequence. And some mathematician came along one day and said, okay, instead of writing out the first term, the second term, they were like, let's just generalize it and use a symbol. And the symbol that they use is a capital A with a little tiny n. And the way that you would pronounce that, is A sub n. So I'm going to say A sub n. And this n represents the nth term in the sequence. So when I put a number there, so for example, A4 would actually represent the fourth term of the sequence. A21 would represent the 21st term of the sequence. So over here in this little chart, you'll see, if I say A1 is equal to 5, A2 is equal to 9, A3 is equal to 13, we could just list this sequence out, 5, 9, 13, 17, and 21. And we would assume that the 5 is the first term, the 9 is the second term, the third term, the fourth term, and so on and so on and so on and so on. We can then also visually see what our common difference is because it's adding the same amount every single time. So we could also say something like the common difference is 4 because it's adding 4 every single time. So one of the most important terms in the sequence is the value of the first term. And we are going to utilize the first term a lot. So I'm always going to be asking you to find A1, and it is literally always whatever is first in our sequence. All right, to determine which type of sequence is represented, the first thing you should always do is determine A1, the value of the first term, A sub 1. If the sequence is an adding or a subtracting type of pattern, then you should find the common difference, or D. If you notice that the sequence is either multiplying or dividing, but remember, multiplying by something, it could be a fraction, we are going to find the common ratio, and remember that stands for R. And if you find something that's adding or you find the common difference, then we're going to be talking about an arithmetic sequence. And if it's a common ratio or it's multiplying by something, we're going to be finding a geometric sequence. The way that I remember this is arithmetic adds A with A. Okay, so if you can remember that the arithmetic sequence adds, whether you're adding a positive or negative, then the only other type of sequence there is geometric, and that one has to be multiplying by something. Okay, so that's how I remember which one's which. So for example 1, we are going to be determining the value of the first term, whether it's geo or arithmetic. If it's arithmetic, find D. If it's geometric, find R, and then extend the pattern out 2 more times. So A1 is always the value of the first term. That should be very easy to find. And I noticed that this seems to be adding by 4 across every single step. So if it's adding, that's a common difference, which makes this an arithmetic sequence. And if I want to extend this pattern out, all I would have to do is 10 plus 4 is 14. And 14 plus 4 is 18, so that would be giving me A5, and this is A6. So I literally am just using that plus 4 to extend the pattern out where it left off. Let's take a look at letter B. Again, A1 is the value of the first term of the sequence, so that's negative 10. But how do I get from negative 10 to a positive 30, then to a negative 90, then to a positive 270. So clearly it is growing, but it's also alternating, and that is because we are multiplying by a negative 3. So our common ratio is negative. which makes an alternating geometric sequence because I'm multiplying by something. So all I would have to do is 270 times -3, that gives me -810. And then if I multiply by -3 again, I get 2,430. That would be the 5th and the 6th term in the sequence. All right, let's do a couple more. So I have 4 to 16, 16 to 28, and then 28 to 40. So A1 is 4, but how do I get from 4 to 16 and then using that same pattern get to 28? I think I'm adding 12 every single time. So my common difference is 12. If I'm adding, that's an arithmetic sequence. And so to get to the next term, that would be 52, and to get to the next term, that would be 64. Last but not least, A1 is always the value of the first term of the sequence. How do I get from 3 to a 1? 1 to a third, and 1/3 to a 1/9. So notice it's decaying. If it is decaying but not by subtraction, then it must be a common ratio of some type of fraction. So how do I get from 3 to 1 and 1 to 1/3? You're probably thinking divide by 3. So if you're thinking divide by 3, what are you multiplying by? You are multiplying by 1/3. So if I want to extend this pattern out, so that makes it geometric, if I want to extend this pattern out, it would be 1/9 times 1/3 would give me 1/27, and then times 1/3 again would be 1/81. That would be the 5th and the 6th. All right, well, these should sound semi-familiar. Arithmetic sequences, if we have some type of pattern like this, 25, 22, 19, 16, and so on, determine A1, so that's going to be, oops, that's already written there, scribble it out, is 25. To get from 25 to 22 and 22 to 19, I am subtracting 3, so my common difference is -3. Use your common difference to extend the pattern out. So A5, if I continue this pattern down, will be 13, then 10, and then 7. I am literally just continuing the pattern by subtracting 3. That's all I'm doing. But now it's asking me to plot these as coordinate points. So you want to think of it as like, okay, what term number is it? Remember, the first term was 25. So that's A sub n, the value of the first term. The second term in the sequence was 22. The third term was 19. The fourth term was given, it was 16. And then we extended it to find the 5th, 6th, and 7th. So 13, 10, 7. What we want to do is plot these points on the grid given. So over 1, up 25, put a dot. Over 2, up 22, put a dot. 3 up 19, 4 up 16, 5 up 13, and if you're going on ahead of me, please don't connect your dots, and 7 up 7. But what I do notice about these dots, remember, we are not connecting them. These were your term numbers, hence why it's labeled N, and these were the values of those terms, value of the terms, hence why it's labeled A sub n. We don't connect the dots. And the reason why is because this is not an XY axis. N, the x-axis is talking about the term number. If I connected these dots, that would mean that there's a number between 25 and 22 if I connected these dots. But there isn't. It is literally the first term is 25, the second term is 22. There's no such thing as the 1.5th term. There's nothing in between there. So that's why actually for sequences we do not connect the dots. We just leave them as basically like a scatter plot. But there is a pattern to it, and I noticed that it sort of represents a linear pattern, a linear by where it's adding the same amount. So hopefully you've already made that connection in your own mind, but now you can believe it. Basically the common difference, D, is essentially the slope. That's essentially what it is. Okay, so we call this an explicit graph when you don't connect the dots. Let's do the same thing for a geometric sequence. So A1 is 2. To get from 2 to 4, 4 to 8, 8 to 16, I had to multiply by 2. And then it says extend my pattern out. So if I multiply 16 times 2, I get 32. If I multiply 32 by 2, I get 64. So now I'm going to plot these points. 1, 2, ignore my dog growling at something, who knows. So it gave me the first term, second term, third term, fourth term, and I extended the pattern out to find the fifth and sixth. So let's plot these points. Over 1 up 2, over 2 up 4, 3 up 8, 4 up 16, 5 up 32, 6 up 64, and that's as far as we can go. And again, don't connect your dots, but notice there's a curve to it, and that sure looks like an exponential growth. It looks just like an exponential function. And it will always look like an exponential function, but it could be a growth or a decay. So depending on if your common ratio is a number greater than 1, it will be an exponential growth shape, or the pattern will grow. If your common ratio, remember, is a fraction between 0 and 1, it will appear to be an exponential decay or something like that, and your R value will be between 0 and 1. So you can essentially call this your growth or decay factor. It's very much related. Just remember, don't connect your dots. All right, see you tomorrow when we dive in a little deeper on arithmetic sequences.